Welcome back to ch305. In this video, I'll be talking about 3 examples that show the cases where there's no solution, unique solution, and n-r parameter family of the solutions. That is basically example 3.7, I'm sorry, 3.5 of the textbook. So if you go to page yes, so page 75, I'll be showing example 3.5, which has actually 3 different cases for unique indefinite number of solutions and a no solution case. Okay, so just a quick reminder, if the system has infinite number of solutions, we can find those infinite number of solutions. That would be through singular value decomposition and pseudo inverse. So that would be a technique that we can see from section 3.10 of the textbook. So if a system has infinite number of solutions, first we have to find the pseudo inverse, which is called a dagger or a superscript plus, right? So after we find a dagger, then through some mathematical formulation, we can prove that the solution would look something like this. Okay, so that is a dagger times b. B is the right side of the equation. Remember, the equation was ax equal b. So that's what we are trying to solve, like this, right? And after we find the pseudo inverse, we multiply by b plus I is the identity matrix minus a dagger a times z. And this z is an arbitrary vector. So whatever you put in z, you get an x, and this x definitely satisfies the equation, the ax equal b. That is why we call infinite number of solutions, because we can have infinite number of choices for z. Whatever you put in z, you can get an x, and that x is definitely a solution. Okay, so we're going to look at an example how we can calculate this. In case there is there's an undetermined system, we have to find the a dagger as I discussed here. There is also a case that the system is overdetermined. Overdetermined means you have more equations than unknowns. Like you have 3 unknowns, you have 4 equations, or you have 2 unknowns, you have 3 equations. In that case, the solution is defined by just the pseudo inverse or a dagger times b. It doesn't have the rest of it, which we talked about for a case that there is infinite number of solutions. Okay, so there are 3 cases. In the case that is the system is well determined, which is the number of unknowns is equal to number of equations. There's a system that is overdetermined, in which we have more equations than unknowns, and there's a system that is underdetermined, where we have less equations than unknowns. So you're going to see all these 3 examples, or 3 cases in example 3.5. So here's the first example. This is called consistent system, where the number of equations is equal to the number of unknowns, and the system has a unique solution. So let's say I have a 3 by 3 equations. These are the coefficient this is the coefficient matrix. You can think of this times x plus this times y plus this times z equals this, and then second equation, and a second equation, and then the third equation. Okay, so the goal is to find the solution, x. So before, maybe from linear algebra or high school or your math classes before, you recall that you have to find the inverse of a, and then multiply a inverse by a. You get you multiply inverse of a times b, and then you get x. So from high school, maybe you learn that to get the solution, yeah, so we do this. Okay, so a inverse times b is equal to, so this is supposed to be the inverse, okay, and the matrix package calculates the inverse for you as well. So we're going to actually deviate from this formula, which we learned from before. This time we're going to say the solution is actually like this. X is equal to pseudo inverse, which we call it a dagger, and then times b. So this A superscript plus is called A dagger. Okay, I'll write it this way. So we're not going to use this. So I just put a red color here. We're not going to use this. We're going to use this, which is green. Okay. So that's what we're going to use in this class. We have to always calculate A dagger times B. So here's A. You can find the A dagger through matrix operation package. I just quickly show you one more time. So you activate the matrix package by clicking on the unzipped file from Blackboard, which I'm trying to do now. Okay, so here it is. I clicked on that and said yes, and then yes. So I get this blue button right here. And then I click on it. I get this menu, move it up to here. And then I go to Pseudo Inverse. I'm going to click on Pseudo Inverse. And for my initial matrix, I click on this 3 by 3. And then the result, I like to get it down here. All right. So this is the Pseudo Inverse, exactly what I have here. So just to show you that you can get that. All right, so the solution is you get this matrix and then multiply it by B. You can do it through matrix package, and if you do that, you get this X. Okay, so I'll just do it very quickly for you. All right, so I'm going to get X here. So this is X. By the way, this is just, I have to actually, so I'm going to move this one to here. That is my A dagger. So let me just copy it here and then paste it there. This is my A dagger, right? And I have to make it superscript. Okay, this is it. Okay, so I'm going to calculate A dagger times B. So what I do is I go to matrix package again. I go to multiplication. My initial matrix is going to be A dagger. And my B is going to be this B, and then the result goes to this cell, and this is it. So you see that those match perfectly, right? This X and this X. All right. So then what you do is, this is the solution. We found the solution. To test it, you can multiply A by X right here. So this is A multiply X. You get this one, which is exactly equal to B. So that matches completely, which means the solution is right. This is a system where we have consistent equations, same number of equations, same unknowns, and the system, the rank of A is equal to rank of A augmented with B. One unique solution. I'm going to look at a system that the system is overdetermined, which means we have 4 equations, right? But then 3 unknowns. So it's a 4 by 3 column now for A. Okay? And this is B. Then we find the A dagger through the matrix package. Then you multiply A dagger by B. So you get an X. Okay, so this is X is calculated by A dagger times B. All right, so let's check whether this solution is correct or not. You multiply this A by this X, it should return B again, right? If the X is the solution, then AX should be equal to B. But when you calculate AX, you see that it's not equal to B. And that is because the system is overdetermined. If you have more equations than unknowns, there's no solution to the system. And so what you get is called least square solution. So the system you get from here, from here, which is A dagger times B, is a solution such that it minimizes the difference between the B that is originally in the equation and then the A times X that we get at the end. So the difference between every element, if you find the difference between every element in B and AX and you square it and then sum them up, that would be the minimum difference you get for this X that is calculated through A dagger compared to any X that you put in there. So that's called least square solution. Okay. So this is for the system where we have an overdetermined system of equations. And then the last case we're going to look at is underdetermined system, where we have fewer equations than unknowns. I have 4 unknowns, 1, 2, 3, 4 columns, but then 3 rows. So that means we have 3 equations, 4 unknowns. And the way we do it, again, is the same thing. We find the A dagger. Now here's the A dagger we found from the matrix package. Here's B. You multiply A dagger by B. Now this time, this is not the solution. We call it base. So this base that I have here is A dagger times B. Okay, this is not complete solution yet. This is part of the solution. So keep that in mind. We call this base. Then we calculate A dagger times A here. Okay, so here's my A dagger times A. This is the identity matrix. And then next what I do is I subtract I subtract A dagger A from identity matrix. So this is I minus A dagger A, right? This is I. This is A dagger times A. You calculate I minus A dagger times A. And then for any Z you put in here, it could be anything you want, you calculate I minus A dagger A times Z. In fact, I'm following this equation exactly. So I'm trying to find the solution using this formula, right? So I calculate A dagger times B, I call it base. I calculate I minus A dagger times A and then times Z. Okay, so the Z is arbitrary. I put here any number I wanted. I put 0, 1, 1, 1. You can put anything else. And we call it arbitrary part. So arbitrary part is I minus A dagger A times Z. Okay, that's the arbitrary part. Then you add base to it. So base was A dagger B, right? So this is base. I just copied over here. You add this and this, you get this solution. And this solution satisfies the equation. If you calculate A times nu x, so this is nu x, right? If you calculate A times nu x, you get exactly the B. So look at this B and compare it with this A times, or the new solution times A, right? So it's the same. So that means now you can actually change your Z and you still can match this. So let's say I'll do, you know, like 2, 1, 2, 2, 1, 0, right? Okay, let's multiply again. So I'm going to recalculate this part with the matrix package multiplication. All right, so I'm going to multiply this I minus A dagger A, and then I'm going to multiply by my Z vector, and then the result will go to this cell. All right, I get a different result. And then when you add it to the base, so you can easily add it to the base, right? You just add these two cells. You see the equation here. If you add these two cells, you get different new solution. But then now let's multiply A by this new solution and see if you get the B back. So I'm going to do multiplication one more time. All right, so here is my A. So I'm going to select my A, right? And then I'm going to multiply by the new solution here. And then the result, I like to get it in this cell, and then run. Okay, sorry, operation missing, and then multiplication. There you go. So you got the same B back. So what I did was I changed my Z, and still I get AX equal B. So that tells us that there's infinite number of solutions because there's infinite number of choices. You have to select Z. All right. So in the last few minutes of this video, I'd like to show you how you can use other operations with the matrix package. Let's say I have a matrix like this, okay? And I want to multiply this by B vector. So you can highlight these three cells, okay? And then you start with equal sign. So I'm typing equal, and you type sys lin, open parentheses, and then you select the matrix you want to multiply, the first matrix, and then times the second matrix. Let's say I want to multiply A dagger by B. Okay, so here's B. I close the parentheses. In Mac, you hold down Command key, Shift, and Enter together, and then that gives you A dagger times B. So I just showed you how you can basically run the solution without using the menu from here, right? I didn't actually use that. I just typed syslin. But make sure before you use syslin, you have to highlight the three cells, or the cells that the results have to go to, okay? You can do the same thing for inverse. I can easily calculate the inverse, or multiply two other matrices, or anything I want using these functions. So in the next video, I'll talk about these functions without using the matrix package menu. All right, so stay tuned, and thanks for watching.